this video, we're going to talk about invertible linear transformations. So first we'll start with some definitions and theorems, and then we'll do some examples. So we're going to start with the identity linear transformation. The identity linear transformation of the vector space W is defined as W into W, which means that I of the identity matrix of W is W, and these are vectors here. So these are vectors. So the vector element in W, when I do the identity on it, it gives me back where I started. This is almost like the do nothing function. The next one we're going to talk about is the invertible linear transformation. So suppose T is a linear transformation from U onto V, and then there's a function S that takes V onto U, such that when I do this composition of S composed with T, I end up with the identity function for U, and T composed with S, so composing it the other way, I get the identity function for V. Then we say T is invertible. In this case, we call S the inverse of T, and we write S as T inverse with this inverse notation. Informally, a linear transformation T is invertible if there's a companion linear transformation S that undoes the action of T. So it's like whenever we do addition, we can do subtraction. When we do multiplication, we can do division. We're undoing that. We always like to be able to undo stuff in math. So we're going to define what an isomorphic vector space is. Two vector spaces U and V are isomorphic if there exists an invertible linear transformation T with domain U and co-domain V, so this transformation from U into V. In this case, we would write U is isomorphic to V, and the linear transformation T is known as an isomorphism between U and V. We see that these invertible linear transformations preserve structure. So that tells us if I have these two vectors, I can add them just directly, or I can do it with a linear transformation and then undo that linear transformation and just add them. So in other words, when I'm doing vector spaces, remember we have the vector addition and then we have the scalar multiplication, that I can consider this addition going in this direction in a very roundabout way, or I can go directly to it. But we're allowed to do that because of it being an isomorphic vector space. Here are some important outcomes from this section where we're talking about theorems. If we have this linear transformation, T is invertible if and only if it is injective and surjective. Remember from the last section we call these bijective. So they have to be both injective and surjective. So sometimes we have to check to make sure that they both hold so that it will be a linear transformation that will be invertible. If T unto U is an invertible linear transformation, then the function of the inverse is also a linear transformation. If T onto V, or the T from U to V is an invertible linear transformation, then the inverse is also an invertible linear transformation, and I can do the inverse of the inverse and get back to where I started, which is T. Now that means also we get our compositions happening, so if T and S are both invertible linear transformation, then that composition will also be a invertible linear transformation. And if T from U onto V and S is V onto W, then when we do its composition, S composed with T, that when we invert it, S composed of T is going to be T inverse composed with S inverse. Notice how that is T composed with S inverse becomes T inverse composed with S inverse. Here is a visual representation of what happens when we go from U with a transformation goes into V, and then the inverse brings it back to where we start with. And any of these here, you can see these entries from the zero vector into the zero vector for U for the zero vector of V, and its inverse brings us back to where we come from. So let's do some examples. Now, suppose that T is defined in R3 and it is mapped to P2, polynomials of degree 2 or less. This is how we're going to define it. We have our three entries in R3, A0, A1, and A2. A2 gets mapped to an x squared, and A1 gets mapped to an x, and then the A0 gets mapped to the constant. We want to show that T is an invertible linear transformation. We want to show that this is isomorphic. So the first thing we're going to do is we're going to go ahead and add two vectors that are coming from R3. So here's my b vector, or here's my a vector, and here's my b vector. And we know from linear transformations that I can add the two vectors first. So I'm going to go ahead and add the two vectors first. And then I'm going to apply the transformation. So the b1 and, or excuse me, the a2 and the b2 is a coefficient on x squared. The a1 and b1 become the coefficient on x, and then here's my constants. And then we know that we can separate out the the a2s and the b2s, separate out by distributing and then combining up my a's together and my b's together, which shows me that it is indeed a linear transformation. So this process holds. So let's see if it holds for the c. So the scalar multiplication, so we do the scalar multiplication. And we know that's a linear transformation, and then we know that from the definition of t that every vector is in P2 is matched up with t, exactly one vector in R3, and that every vector in R3 is matched up in a vector in P2, therefore t is 1 to 1, and onto this it's isomorphic. So we have shown that R3 into P2 is isomorphic. Let's take another look at another example. Suppose we have, we're in C3, so we have 3 entries, now we're in complex numbers, and we're going to define it by going into a matrix of 2 by 2 size, and this is how we're going to define it. Determine if T is a linear transformation. So we're going to choose an arbitrary matrix, we'll call it A, where I've got 5, 3, 8, and 2. And then T has to be mapped to the T that takes my C3 vector, has to be mapped to these entries. So my A minus B has to equal 5. My 2A plus 2B plus C has to equal 3. My 3A plus B plus C has to equal 8. And negative 2A minus 6B minus 2C has to equal the 2. Then if we solve the system of equations, we find that it's an inconsistent system, which means that I found a matrix in R2, or excuse me, a 2 by 2 matrix that is not in the range of the linear transformation. And so by definition, that means that it is not going to be invertible, because remember, it has to be onto and it has to be 1 to 1. And we've shown that it's not going to be both onto and 1 to 1. It fails. So here's some more definitions and some more outcomes. So the definition, the rank of a linear transformation. Suppose T is a linear transformation from U onto V. Then the rank of T, noted as R of T, is the dimension of the range of T. So when we're talking about the rank of T, we're talking about the dimensions. And if you remember, the dimension is the number of basis vectors that we have. So the rank of T is the dimensions or the number of basis vectors that we have in the range. So the rank of T will equal the dimensions of the range of T. And then the nullity of the linear transformation. Suppose that T is a linear transformation from U into V. The nullity of T, noted as N of T, is the dimensions of the kernel of T. So the nullity of T is equal to the dimensions of the kernel of T. So here's some important theorem outcomes from the section. If U and V are both isomorphic vector spaces, then their dimensions have to be equivalent. This also means if they don't have the same dimension, they are not going to be isomorphic. So that was back up here. If we had that information prior to this one up here, we could have said that they weren't going to be isomorphic because we know that the dimensions of C3 is 3. It takes 3 vectors with 3 entries to form the basis of C3. And the dimensions of a 2 by 2 is actually 4 because I need 4 matrices in which I have a 1 in a different position each time and zeros everywhere else. And so we knew if we had that other theorem outcome that we could have stopped right at the very beginning and said, wait a minute, they don't have the same dimension, so it may be a nice linear transformation, but they're not going to be isomorphic. Then we have a couple of more we want to talk about. So if T is a linear transformation from U onto V, then the rank of T is the dimensions of V. The rank of T has to be the dimensions of V, if and only if T is surjective. So this goes with the whole 1 to 1 and onto. So, and this follows this one as well, is that T is a linear transformation, then the nullity of T is 0. The nullity of T is 0 if and only if T is injective. So that gives us that, hey, let's go check the nullity, and if it equals 0, then we will be able to start talking about dimensions, we'll be able to start talking about isomorphisms. So if the nullity of T is not 0, then it is not injective, which means it won't be isomorphic. If the rank of T, the dimensions, is not equal to the dimension of V, then it's not surjective, which means it's not going to be isomorphic. If T is a linear transformation, then the rank of T plus the nullity of T must equal the dimensions of U, the vector set we start out with. If V is a vector space, then the dimension of V is equal, and the dimension of V is equal to n, then V is isomorphic to R of n. So that's another little tidbit of useful information. And then if we think about when we first learned rank and nullity of a matrix, we know that the rank and nullity of the matrix must sum to the number of columns of the matrix. If we consider the linear transformation of Cn into Cm defined by the m by n matrix A, where we defined it as the linear transformation of A times x, x being the vector coming from Cn, the range and the kernel of T are identical to the column space and the null space of the matrix A. So the rank and the nullity of the matrix are identical to the rank and nullity of the linear transformation T. Then the dimensions of the domain T is the dimensions of Cn, exactly the number of columns for matrix A. So it's really kind of nice to kind of bring in all these things that we have been looking at piece by piece and kind of bring the pieces together. So let's look at this one. We have, suppose that T is a linear transformations of polynomials of degree 4 or less, and it's going to transform into this 3 by 2 matrix, and this is how we're going to define it. Determine if T is an invertible linear transformation. The answer is no, because the dimensions of polynomials of degree 4, including the constant, is 5. The dimensions of a 3 by 2 matrix, again, moving the 1 in a different position and zeros everywhere else, is 6. So there's no way that these are going to be isomorphic. So we could check to see if it's a linear transformation if we wanted to, but it's saying it is, so we're just going to say, hey, it's not isomorphic because their dimensions don't match. So that's also a nice quick little check. Now let T be a linear transformation where polynomials of degree 1 or less, so just linear, literally linear polynomials, and into R2. This is how we're going to define it. So P of x is going to be the P0 or P1 or P0 and P1. So we want to determine if it's an invertible linear transformation. So we're going to check to see if it is a bijection, in other words, that it's 1 to 1 and onto. We're going to list out the elements of P1 that are polynomials of this form. So P of x equals ax plus b, so that P0 is equal, or P of 0 equals b, and P of 1 must be a plus b. Therefore, the transformation of ax plus b would be b in this first position and a plus b in the second position. So for any real numbers c and d, the vector equation b is equal to cab plus e is equal to d has a unique solution. Therefore, t is 1 to 1 and on to. Moreover, that unique solution shows us how to find the inverse. So R2 back into P1, since A equals D minus C and B equals C, it follows that this would be the transformation from a linear equation into this size 2 vector space, or the vector size 2. And so we have this inverse. Now we can check it also by computing. So I'm going to do the inverse of the composition of the inverse with itself. So here's a composition of the inverse with what we started out with, how we defined it, and we end up with ax plus b. And then we're going to compose the other way, and we end up with this, and so we're done. If we're asked to find the matrix M, in this case we're asked for the matrix M, that of the linear transformation, given that this is the linear transformation. So I'm going to take some vector x, I'm going to multiply by this matrix A, and then multiply it again by x. And that's how I'm going to consider this linear transformation. This is really just asking us to see whether or not we can invert this matrix, and we can. And when we invert this matrix with a regular 2 by 2 matrix inversion, we end up with this. So that's it for right now. We'll do some examples in class, and other than that, we've now almost finished the quarter up.